First up, we have Brianna Bermudez, Brandon Grimaldo, and Sofia Marquez. Brianna is a physics major, and a fun fact about her is that she likes to do long distance running. Brandon is a computer science major, and a fun fact about him is that he puts money he put money in a vending machine at Foothill and it scammed him. He never got his drink. That is the story of everyone. I have also given up with the vending machines at Foothill. And Sophia is a physics major. And a fun fact about her is that she used to attend astronomy lectures at Foothill with her dad when her dad was a student. Awesome. Love that. So all three of our students mentored with Sophia Sheikh, who is a researcher at the SETI Institute, and they will be presenting their presentation, Measuring Pulsar Scintillation with the Allen Telescope Array.
Okay, well, thank you for the introduction. My name is Sophia, and today with Brianna and Brandon, we're going to be presenting our research on measuring pulsar scintillation with the Allen Telescope Array. So let's begin with discussing what a pulsar is. First discovered in 1976 by PhD student Jocelyn Bell and her advisor Anthony Hewish, a pulsar is a neutron star, which forms when a massive star collapses and becomes very small and very dense and is composed primarily of neutrons. Because of their small size and their high density, these stars rotate really fast, and from either end of their poles, they emit radio waves, which we then capture with a radio telescope. So if you're having a hard time visualizing this, the easiest way to think of this is to think of a lighthouse, which is an analogy our mentor gave us. So I'd like you to turn your attention to the top right of the screen and think of the lighthouse that you see there, with two rays of light emitting and rotating periodically out to sea. Pulsars work very similarly as they rotate and radiate radio waves from either end of their poles, and if they're in the right orientation, they reach us here on Earth, which we then capture with radio telescopes. Okay, so let's discuss what scintillation is. In order to understand scintillation, we have to understand the interstellar medium, or the ISM. And though it sounds complicated, the interstellar medium is a name for all the gas and dust that's floating and moving throughout space. Scintillation is the measurement of this gas and dust. And so when pulsars shine their light, scintillation is the result. So if you look at the graphic on the bottom of the screen, you'll see a pulsar that's rotating and emitting radio waves. Those waves are passing through the gas and the clouds in the middle, which is the interstellar medium, which then distorts the waves, which we receive here on Earth, which will tell us how much and what kind of gas and dust is between us and the pulsar. So measuring scintillation is useful for getting accurate readings of the interstellar medium, which is essential for projects that require precise timing or distance measurements that need to take into account the effects of the ISM. This would be for projects like NanoGrav, which is an international collaboration to study low-frequency gravitational waves. These low-frequency waves can come from events like supermassive black holes merging at the center of galaxies, or possibly even the aftershocks of the birth of the universe. These low-frequency waves are too small to be detected with instruments on Earth, so scientists theorize that we can use pulsars as our instruments of measurement. The way this works is that pulsars rotate with extreme regularity, meaning that it's easy to predict when we expect to see a pulse coming in from a pulsar. If NanoGrav takes a look at pulsars whose pulses are coming in either a few seconds early or a few seconds late, and they're able to determine whether or not this could be from a low frequency wave by taking a look at measurements of scintillation. Scintillation could distort the timing of when the pulsar's pulse is received here on Earth. So it's important to know whether the timing is off because of a cloud of dust or if it could be from a low frequency wave. So part of the work that we've been doing for the last few months has been with the Allen Telescope Array, which has been taking long-term observations of pulsar scintillation, which has never been done before. In addition to that, we are also observing our pulsars about once a week, which is 2 times as more often as previous studies. These long-term and frequent observations of pulsar scintillation are extremely important for projects like NanoGrav. And in fact, we're actually sending our data of pulsar scintillation over to them for them to use in their project. If you take a look to the bottom right of the screen, you'll see a picture of the Allen Telescope Array, which is where we are receiving our data on pulsars. There are 42 dishes, each about 20 feet across, run by the SETI Institute. These dishes have a large bandwidth with really good frequency resolution, meaning that we're able to receive lots of frequencies at once, as well as lots of pixels within those frequencies, meaning that we're getting really clear images. And with that, I'll pass it off to Brianna.
Hello. So now that we know what pulsars and scintillation are, we can get into the data analysis portion of our research project. In fall 2022, we collected 60 pulsar observations, 16 of which are unique pulsars. Each ran with an interval of 30 minutes. The pulsars are brightest at the lower frequency, and the frequency intervals that we took our data with were between 900 and 1600 megahertz. To give you some context, that's like a GPS. A GPS is about 1200 megahertz. This picture on the right is another picture of the ATA satellite dish. One of the first things we did was look at pulse profile graphs. As Sophia mentioned, the lighthouse effect. This is what the lighthouse effect does. Sorry. Okay. When the pulsar is hitting the Earth, the light emits, and then this is when we get the peaks. The first graph is an example of a really good pulse profile graph. We want to look for tall peaks with not much going on at the bottom. On the x-axis, we see 0 to 1. That means it's one rotation of the pulsar. The second graph is a good example of a bad pulse profile. So you see a sine wave-like function with jagged lines. And this could be due to the pulsar being really faint or RFI. So what is RFI? RFI is radio frequency interference, which is a human-generated signal that comes from Wi-Fi, cell phones, GPS, and other things like that. We could see the pulsar very faintly to the right, and the RFI are the horizontal lines. And what we can do to try to brighten the pulsar is to use a tool called PASI to zap the pulsar. To zap the RFI, sorry. So here is the first example when the pulsar was very faint. And after using the PASing tool, we see that the pulsar becomes a lot brighter between 1100 and 1300. Okay, so after PASing the pulsars, we started with, we had 16 pulsars, and the success rates were, they weren't the same after PASing. Like, we only had 34 out of 60 good files worth analyzing after the PASing. And I'll pass it on to Brandon.
So here we use a model of the galaxy, which is the graph on the top right. And to prioritize which pulsars we're going to use for the scintillation bandwidths. If a pulsar is located further away from the center of the galaxy, so at the edge of the spirals, it may be less affected by the dense gas and dust, leading to a potentially wide scintillation bandwidth. On the other hand, if a pulsar is located closer to the center of the galaxy, the dense gas and dust in the region can diffract the pulsar radio emission. And then this leads to a potentially narrow scintillation bandwidth. And we use the predictions from the NE 2001 galactic gas density model to predict which pulsars will have bandwidths that are not too wide or too narrow for us to measure. And given the frequency resolution and bandwidth of the ATA, 23 pulsars passed this test, and we use them for the first step in the next process. And then in the context of pulsar scintillation, a dynamic spectrum, which is the one on the left, which shows a bit of, what's it called? A patchiness. It's a two-dimensional representation of the intensity fluctuations of a pulsar's radio emission as a function of both time and frequency. And then to create a dynamic spectrum, the radio signal from a pulsar is recorded over a range of frequencies and over a period of time. So the intensity of each frequency component is plotted against time to create a two-dimensional image known as a dynamic spectrum. And then we continue with the 2D ACF, which is a 2D autocorrelation function, which is a math tool that helps us quantify the degree of correlation between the intensity fluctuations at different frequencies and times in the dynamic spectrum. By calculating this, we can determine the characteristic time and frequency scales of the scintillation patterns. And then by calculating the scintillation patterns, we want to find the characteristic frequency scale or scintillation bandwidth, which is represented as a bright centered horizontal band. The wider it is, the larger the scintillation bandwidth. And then for the third step, the Gaussian fit, we can measure the width of the bright band in the 2D autocorrelation function with which can determine its width, and also relate back to the properties of the interstellar medium. And then the next step for this project is completing the scintillation bandwidth measurements for as many of the 34 files as possible. And the reliable pulsars will be used for a future campaign with the ATA, whose measurements will be shared with Nanograv to improve timing models. And then some of the challenges I faced was the complex GUI and wait times for the data, and also deciphering what the graphs meant and making difficult judgments on whether or not they would be worth extracting data from. And then for my reflection, I learned how to use MOBA Xterm and Jupyter Notebook applications, which take a long time to set up, as well as learning what the graphs given, how to read the graphs given, and how to extract meaningful information from them. Some insights I gained was a realization that it would be nice if everything was automated with one click of a button. And then you see on the top right, all the stuff we had to go through in the process. And I definitely was less intimidated by internships and meeting new people in general. And I found it very important to reach out to my mentor and everyone else for help. And it also made me realize I'd like to pursue a career in programmable automation to automate and streamline everything, like on the top right, to make it like one click of a button, to simplify it and make it less of a headache for everyone. And then, of course, thank you to our mentor, Sophia, and the rest of the SLI team. Thank you, Sophia, Marissa, and Meloni for the guidance and help. Thank you.